Hello, my name is Michael Poplick, and this is Lizzie Davidson, and here's our Project 3 FEA heat transfer and fins. First, we just want to talk about a brief overview of what we're going to talk about today. We're going to start with the design statement, go into the problem-solving method, take you all through a little walkthrough of ANSYS, provide you with our solutions, talk about our analysis, and then finish with our conclusions. So first is our design statement. We were supposed to study the rate of heat transfer for a basic fin geometry. We were given the parabolic number 2. We were supposed to identify its maximum size, pick a base that will push the limit of the 1D assumption, use ANSYS workbench for the analysis. These fins were used to cool a surface at 150 degrees Celsius and maintain that temperature. And we were supposed to do this with 3 different materials: aluminum, copper, and stainless steel. The ambient temperature we were supposed to remain at was to be 20 degrees Celsius. We were given a convection coefficient of 60 watts per meter squared times Kelvin, and at the end of the day we're supposed to verify the accuracy of the 1D assumption on the models versus the textbook. So our problem solving method was as follows. We researched and gathered information on parabolic fins using the textbook. We used a square base and took a guess at the length of the parabolic fin. We modeled our geometry on the NX CAD software, picked steady state thermal analysis in ANSYS, imported our geometry into ANSYS, then inputted our constraints and solved. We drew our conclusions, modified the length and size of the base, and then ran the program again. We iterated until a satisfactory solution was found. So like we talked about earlier, first we created our geometry and then we imported this, and then the first thing we did was put a mesh on it. After that, we added our temperature on the back, top, and bottom sides of the square bottom of the base, and the next convection was added to the entire object with a provided value of H and ambient temperature. Here's our result for our first iteration. We ended up finding out that it was way too small, so we ended up making a bigger one. Our result for the stainless steel with the new geometry is as follows. For our solution for copper, when compared to the stainless steel, actually took a lot longer to cool down. We'll see that when we go to the graphs later that it is because it has the highest conductivity of all the materials. And last but not least, this is our result for aluminum.
After many iterations, we had to look at our results and determine the length at which the fin reaches T infinity, but not too long, which would result in material waste, excessive weight, and increased costs, but we still wanted to have it where it was at a high heat transfer, but still getting close to T infinity. From this, we chose a length of 5.5 meters, which approached T infinity while still having significant heat transfer. Here are our analytical results. Compared to the finite element analysis, the numbers are slightly off, but it still shows that copper has the slowest temperature drop and has the highest heat loss, whereas stainless steel has the lowest heat loss but approaches T infinity the fastest. The solution for the optimized length could be found with enough iterations more accurately than our guess and check method. Optimized length varies for each material, with stainless steel cooling down the quickest and copper cooling down the slowest. Copper is the highest conductivity of the 3 materials, so conductivity is indirectly related to the length of the fin required.